situation. Now I'm going to do 26. May I erase this?
Yeah.
Anyone have 18?
No.
The only
No.
kind of weird thing about that is that when you divide the 2 root 3 by 4 is that it's really, for me, it's not obvious what the answer would be.
Understood. We'll talk about that one-on-one a little later. It's not dividing again. Please say factoring. That may help if you start thinking of it as something different than division. Because it is. 26.
1
Okay.
minus I square root of 5.
Okay. 1 minus I square root of 5. Is there a square root of 5 anywhere on the unit circle?
No.
No.
Yes. Maybe.
So, this is not going to be one you know by hand. So, I would say the first step would be, I'm going to go ahead and draw it just for fun. 1 over down square root of 5. This is so not to scale.
Oh, that's okay.
There's my theta.
Hold on.
Yeah.
How do you know which way can it be negative 5 on the axis and then just that kind of triangle?
No. It's a radius.
No.
You know,
That,
you mean draw from here to here?
no, draw from the 1 to the dashed. The 1, no.
One where?
Oh, yeah, no, from the 1, yeah, the 1. Other side,
Here?
down.
Down?
Yeah.
No.
Why not?
Because the hypotenuse is always a radius. The hypotenuse is always like a clock hand. Okay? And a clock hand is always centered at the center of the clock. So the hypotenuse always comes out from the center to some point. Always comes out from the origin. So that's okay, so this hypotenuse now, r, is going to be the square root of 1 squared plus the square root of 5 squared. What's the square root of 5 squared? 5. So that's root 6.
Where did all that come from? You just did the Pythagorean theorem?
Yep, just the Pythagorean theorem.
It's like the vector.
It's how you just like the vectors. It's how you always find a hypotenuse. We were just calling this, saying the radius was like a hypotenuse, so got to use the Pythagorean theorem.
The square root of x squared plus y squared.
And while we're on the triangle and just like vectors, bandwagon, if I want to find theta, theta is going to be the inverse tangent.
Of y over x.
Yep, the opposite over the adjacent. So that's going to be root 5 over 1. I have no idea what that is without a calculator. None.
Can we just leave it like that? Well,
Wait, but isn't that just root 5?
Yes, but I still don't know what the arctangent of root 5 is. Not really, because your final answer has to be r cis this number.
Wait a minute.
And I'd rather you not leave it like this for your theta. So what? Give me a number for
65.9.
60, and that's negative down here. Could you do 360 minus that?
294.1.
294. So I would say, in polar form, z equals the square root of 6 cis. What was that number again?
294.
294.1 degrees.
Wait a minute, I put my answer as like r equals and then theta equals.
In polar form, you're supposed to write it this way.
Oh, I thought it was like because I was doing r and theta, so I thought it
Oh,
was
like polar form for non. That's polar real. This is polar complex.
Oh.
I know we've done rectangular real, rectangular complex. Now we're doing polar. Then we just did polar real. Now we're doing polar complex. And for polar complex, you have to write it as the radius cis, the angle. This is the cosine plus I sine thing we did yesterday. Good times.
Yeah, they were. Okay, thank you.
All right. Okay. Today we are going to begin now. New notes. Deep cleansing breath. Okay. We're going to begin some operations with these, and we are going to compare this to the operations with imaginary numbers you learned last year in Algebra 2. Yes.
Are we on a test on this? Or is it exam?
We're going to have a test on this on Tuesday, and Wednesday, Thursday, Friday, we're going to review our little rear ends off.
What are we going to test on?
But this test will only be on this. We're learning one new thing tomorrow, 2 days of review. It's just on polar complex, nothing else.
This exam should be fairly easy, right? Since we didn't do that much. We did like 5
Yeah, yeah. It will. Anyway, let's get to the actual material.
That doesn't necessarily mean it'll be easy.
Okay, well, see what you think after this. Polar complex operations.
Oh, everybody have
It's a
polar
pen.
and complex.
This is a pen.
Because this is polar complex. It's not polar real. Okay, now, polar complex operations. What we've got here, we're going to start with addition. That's where most number systems start. And I think you'll actually like this one. Let's review rectangular for a minute. For addition in polar rectangular, and this is true of subtraction as well, you add the components. Every complex number is said to have a real component that we label A, and a non-real or complex component we label B. So we have our real and our non-real. If you want to add two imaginary, I try and stay away from that word imaginary. If you want to add two complex numbers, you add the components. So in rectangular form, if I say what's 3 plus 5i plus 2 minus i, what do you think the answer would be?
Oh, so it's 5
plus 4i.
plus 4i.
Yes, 5 plus
I got it before Alma.
4i. Congratulations. 3 plus 2 is 5. 5i minus 1i is 4i.
So I can beat her there.
You just add the components. Okay?
Thank you.
If I put subtraction here, you make sure to distribute the subtraction before you work it out. Okay? Now, listen very carefully. In polar complex form, you don't bother with addition or subtraction. You change it to rectangular and do it this way.
You suck.
There is no good way to do polar complex
Wait,
here.
is this
It has
like
to be
polar
wet.
plus complex, polar plus rectangular, or what?
This is just rectangular here.
So why does it say polar rectangular?
Because this is, I am terribly sorry. I am terribly sorry. Kathleen just pointed out something important. This was supposed to be complex rectangular up here. Thank you, thank you, thank you. She should, oh, you all should have caught that. This is complex rectangular. So for addition and subtraction, you just use the rectangular components. Here's where that can get to be a little bit of a pain. You may or may not need your calculator for it. This is probably a calculator question. Parker, you're following me over here? Mm-hmm. So if I say what is,
Parker, good job.
if I say what is 5 cis 45 plus 3 cis 60. Remember where this comes from with the cosine plus I sine. So what I would say is, okay, what's the cosine and sine of 45?
Root
2
2 over
over 2.
2 over 2. So this is 5 root 2 over 2 plus 5 root 2 over 2i.
And this is polar?
This was given in polar, and now I'm changing it to rectangular.
Do you have to change it?
To add or subtract, yes. Add or subtract you can really only do in rectangular.
That kind of sucks.
Well, it's a lot easier if you have to do it at all. In this case, it's a little annoying, and I'd pull out my calculator. Now, what is the cosine of 60 degrees?
1/2.
3 over.
Cosine of 60.
3 over
1/2.
2.
Cosine of 60.
I said 1/2.
I said it 3 times before you.
Thanks, guys. Cosine of 60 is 1/2.
I said
So this is going to be 3 halves
No, he didn't.
plus, and what is the sine of 60 degrees?
Root 3 over 2.
So this is going to be 3 root 3 over 2i. And if I ask you to do this, I'm going to give you a calculator, and you're going to pull out your calculator and get decimals,
No, we're not.
and you're going to add the real and add the complex components.
Wait, can it be...
If I didn't give you a calculator, you'd pretty much be stuck at the 5 root 2 plus 3 over 2
Yeah.
plus,
So why can't we just do that?
you can do that.
Root 3 over
No, even if we have
5
the
root
calculator.
2 plus 3 root 3
Even if we have the calculator.
i.
Yes.
Yeah, so if I didn't give you a calculator, you'd be done there.
No, but what if we do have a calculator? Can we still leave it like that?
Read the directions carefully. If I say round your answer to 2 decimal places, then probably not.
Mr. Belvo,
Yes.
can't you just write 5 root 2, like all of that over 2?